Hello friends, welcome to my channel. Today we'll discuss about trait. Trait is one of the most important foundational component inside Rust ecosystem. Inside Rust, you'll find uses of trait in many places. In a high-level mental model, you can think trait is similar to with interfaces, but there are some obvious differences. Using trait, you can define a method signature, but not the concrete implementation. It is a kind of contract between various different components or a specification, whether that individual component needs to provide this concrete implementation for the trait. Now let's get started. We have defined as simple struct point and we have created as instance p1. And we define a trait shape. Inside this we can provide any number of method signature. If you notice here, there is no concrete implementation for it. The signature is similar with the normal function. It can take any number of input arguments or return type. In our case, print is a function which take immutable reference as a self, but there is no concrete implementation provided for it. At this moment, the point and shape are disjoint with each other. There is no relationship between those two. And if you remember, in this IMPL point, we can provide any kind of methods related to struct. In this case, new method which take two argument xy and create an instance of point and returns it. Similar to the struct implementation, we can create IMPL shape for point. At this moment, we are providing the implementation for the trait shape. If you do IMPL shape for point, then point and shape are being associated with each other. And inside that, we are providing this opportunity for providing implementation for print. We can define like different struct, for example, point, rectangle, square, and so on. And each needs to provide similar implementation for it. And inside this block, self will point to that individual struct, whichever we are providing implementation. In our case, self is pointed to point. This is the immutable difference or read-only access. So inside that, we are printing x and y value. Once we do that, we can access the print method using p1.print. And whatever the functionality we provided as part of the trait is getting printed. This p1 x equal to 1 and y equal to 1 is printed from this particular trait implementation. And as you are aware, like we can create like point new, this is a constructor p2. Now let us discuss about two important foundational components of trait. So as we are aware, like this trait shape can be used as a function return type. We can inside that block, we can create an instance of point or rectangle or square and so on. How we can return it? There is a two way to return it. One is dynamic dispatch and another one is static dispatch. Both are slightly advanced concept. I'll touch upon it today and I'll explore it in detail in future videos. So I have created a favorite shape function. It looks very simple as function like x and y, two argument it takes, and inside that it instantiate a instance of p. But important thing to note over here is that I have wrapped this point struct instance inside a box type, and because point contain two primitive data type x and y, which are both signed integer values. So instance of p only allocated in stack. There won't be any heap allocation. But box is a smart pointer which allows us to allocate memory inside heap and returns a pointer. And if you see this return type, we are providing box and dyn stand for dynamic. and trait name. So inside this box, if you use box, it will return a dynamically allocated trait. So in the runtime, it is a unsized implementation. That means in the runtime, you can change from point to rectangle and so on. Or you can try to return a different implementation of box. Oh, sorry, shape by wrapping into the box. So in the compile time, you may not know which particular instance you are trying to return. This is not a dynamic dispatch. In the runtime, the behavior may change. This is a simple example. In this case, all the time we're returning point, but there may be possibility that in future you may want to return some rectangle based upon some condition or depending upon some inputs. So even though it is a box just a wrapper, you still using this p3. If you notice over here, it is not a simple point type, but still because you are because this box contain this implementation of shape, you can still call this p3.print methods. And it is one more example, random shape. Here we could have passed any input argument, but the sake of clarity, I have avoided passing any input arguments. And in this case also we are instantiating point. But if you notice over here, there is no box over here. We are directly creating an instance of point and returning it. So in this case, IMPL shape. This is a static dispatch. Means in the compile time itself, we know exactly what we are trying to return based upon some input. It can't be dynamic. So there are subtle differences between those two. And this point instance is created in stack memory, whereas box is always allocated inside heap. So the size of this particular return type you know in the compile time, but in case of box you don't know how much memory you are going to allocate into a heap, so that allocation may expand or shrinking. So this is dynamic dispatch and this is static dispatch. So P4, if you notice over here, the type is IMPL shape, and in this way also we can create like P4.print. Now we'll discuss about providing some implementation for default trait provided by Rust, and this sometimes known as operator overloading. We provide our custom functionality for the operator, for example like plus or equal to. Now let's see how we can use it. To get started, I have defined as point struct again. And we have created two instances of point, P1 and P2. And if you try to compare like P1 and equal to P2, it will throw compile time error. Because binary operation equal to cannot be applied to type point. This equal to operation can be applied to integer, floating point numbers or string by default, because Rust provides the implementation for those. Because point is our custom type, so Rust doesn't not sure about what to do when it encounter equal to symbol. But to provide an implementation, it is simple. If you see an example, must implement partial equal. So partial equal is a trait. If you provide an implementation, so the Rust compiler will recognize what to do with equal to symbol. So there are different ways to do that. I'll show two examples demonstrating both to provide a implementation by ourselves and to use derive macro to provide like implementation for partial equal. So as we provide implementation using derive debug macro, similarly we can use partial equal, and Rust itself will expand and provide implementation and compare this x and y value by itself. So we don't need to write any logic for that. Once we derive this partial equal, then this Rust compiler will recognize equal to and compare between individual values. In our case, it is false. Now let's see another example. If you try to add P1 and P2, this plus also is not recognizable. Cannot add point to point. So for that also we can provide an implementation for trait, so that we can able to provide an functionality for plus operator. This plus is known as operator, and this kind of providing this functionality in this manner is known as operator overloading. So this trait name is add for point. So we are providing implementation for add, and this output will point to point. This is associative type. If you see this signature, we cannot change. The signature is provided by the add trait itself. So we have to only provide this implementation itself, and this VS Code and this kind of extension will help you to provide this skeleton for it. So you need to worry about only this part. So in this case, add self and other point. So this is the instance where you are calling add. The left hand side like P1, and this other is the P2. And once we add P1 and P2, the return type also a new instance point. So in this case, we are adding the self.x plus other.y, other.x, and so on. So you are free to provide any kind of custom implementation as you desire. But it is still not printing because this add is not found in the scope. So there is an instruction or hint provided. We have to import this particular package from a standard OPS module. Now let's do that. Once you import, that error is gone. And we can able to add 3.0 and 4.0 as 3.4. If you want to add, if you want to change its values, so P3 is becoming the summation of this individual component, X and Y, 13 and 14. So in this manner, you can do operator overloading and provide some implementation for the default standard trait. For example, PartialEq and Add. In this way, you can expand or provide additional functionality for the standard trait to your custom structure. Now let's discuss about iterator trait. Iterator trait is very useful in kind of looping through a collection of data, or it can be used also in conjunction with counter kind of data structure. Now let's see one example of default iterator, how it is being used. Also, we'll try to implement this iterator trait to provide a custom functionality. We have an array of character as alphabets. So using this .iter, we can get this iterator. This iterator needs to be mutable because once we call like next function, so this iterator is getting modified all the time. So that data will be removed from the iterator. So we can call this next element iterator.next. It will point to A, B, C, and finally it will point to none. But if you see this interesting thing, this iterator.next is not going to return the data itself. Rather, it will return an option type. Option is a kind of enum which contains some with payload and none with no payload. So if there is no data, it will return none. If there is some data, it will return some along with the payload. This is the standard behavior of iterator, and it is being used heavily across all the Rust ecosystem. Now let's create our custom struct and see how we can provide an implementation for iterator. So we have created our custom struct counter, which have two fields, current and next. Current will be initialized to 0, and once we call this next, so it will be increment next would point to 1 and 1, 2, 3, 4 and so on. So we'll use as a kind of counter or incrementer. Now let's implement the trait. So IMPL iterator for counter. This iterator is available inside our trait, inside our standard library. So we need to import it. In standard iterator module, this iterator trait is available. And one function we have to provide implementation next. Next take one argument, mutable reference. Because next is usually able to change this underlying data. And this item is associated with array. And if you see this current implementation next, we are incrementing to 1. And we are returning this current values. We are not, this next and this next are different. In this case, you can use anything else, like future data or something like that. But this next you cannot change. Each iterator, we have to provide as implementation for that. And this is like which data you want to return. If you are returning a counter type, so you have to provide this item as a counter here, or some different type, or you want to return some kind of floating point numbers and so on. But in our case, we are returning current data. So here it is pointing to self item. This item is associative type. So important thing to note here that you have to, the input argument of next function is a mutable reference, because it is changing this current and next data. Next it is incrementing to 1, current it is storing this previous next value, and it is returning the old current data. Once you do that, we can create like counter instance and counter instance, because it is, we don't need to call iterator again, because counter provides this implementation trait. We don't need to call dot iter to get this iterator, because counter itself is iterator. And we can use range. Underscore means we are ignoring the data. You could have used I, they or something like that to define, store the value. But because we are not interested into that 0 to 5 value, we are ignoring it. This loop will run for 0 to 4. So if you see this next, 0, 1, 2, 3, 4 is printed. And it won't print none this time, because there is no breaking condition. Our counter will keep on incrementing. And if you try to debug this counter value, so it will print, this counter will contain this current as well as next. If you do next, it will only return this previous current values. First time it will return 0, 1, 2, 3 and so on. But under the hood, it will have the value of current as 5 and next as 6. So once you do next, it will return this current value 5 and increment both of the thing. So this is the way usually we provide an implementation for iterator. Now let's discuss about copy and clone trait. With respect to our own structure, usually this copy and clone are already defined for primitive types, for example, integer, floating point numbers, character, etc., and also string type. But we'll create our own structure and we'll explain about the difference between the copy and clone functionality. So as usual, we create our point struct with debug macro associated with it. So we can do, if you try to call p2.clone, then we will get compile error. It mentions about no method named clone found for the struct. Clone is usually helpful for allocating a different, for example, the type, for example, string with capital string type, which allocate the memory inside heap. And clone, if you do string.clone, then it will allocate and another heap memory location and copy the content to it. So it will create a duplicate. It has some performance issues But as you are a beginner, you should not worry too much. You should use clone liberally wherever you need it. But in our struct, both x and y are like a primitive data, so there is no heap involved here, heap allocation. But if you create like y as a string data type, then heap allocation will be allocated. In that case, this p2.clone will create a duplicate of it. Even though it is a stack memory allocated, you want to do p2.clone, so a duplicate copy will be created in a stack. So it is a cloning of the p2 instance. But if you want to provide, there is a trait known as clone. We can provide implementation for that. Either you have to provide your own implementation, or using this derived debug macro, we can provide like clone default implementation. Once we do the default clone implementation, this error is gone. Now this p2 cloning is successful, but it is complaining about another pointer like p1. In this case, once you create p1 instance, and in this line if you do equal to assignment, then p1 is data by default is moved to p1 to p2. If you use like this assignment operator for primitive types, integer, floating point, then it won't complain. By default they are copy trait. They provide an implementation for copy trait. Copy and clone are a bit different. So now let's provide a copy trait implementation for our p1 for our point as well. Once you provide a copy trait implementation, there is no error, and this p1 the content is copied to p2, and both p1 and p2 are available at later point of time. Now let's discuss about some of the similar concept of trait inheritance. How we can have a parent and child trait, and how we can will try to resolve some of the issues, interesting challenges we'll face in that pattern. We have created a custom trait employee with 3 attributes of field: name, role, and language. And we have created a EMP instance of it. Now let me define a trait person, which is my name for function signature, which take immutable self-reference and return a string literal. So whichever, if you try to provide an implementation person, I just want to return that employee.name. And we have called a programmer trait. If you see this, there is a colon here. So whichever the function is available in this by name is by itself is if you provide an implementation programmer and you pass as an argument using programmer trait, you have access to both my name and my language as well. So in this case, it is a similar signature with this person my name, which return the language as a string literal. Now let's provide the implementation for both of them. So IMPL person for employee. This is the method signature, and we are returning self.name. This is a simple example. And in programmer, we can return this self.language. And let's define a function print employee info, which take one argument EMP and it take a immutable reference. In this case, we have given like programmer. This is like static dispatch. We have not using dynamic dispatch, for example, box and other type. So which take any whoever implement this programmer trait, in our case employee, or it may have some other struct also can provide this implementation. But using that emp.myname and emp.mylanguage we can access. But if you notice, like this programmer trait is only provide implementation for my language. But because person contain my name, so we can access using emp.myname that functionality as well. So once we call this print employee info, we have to pass this reference, and this name as well as this programming language will get printed. In this pattern, there is an interesting challenge known as diamond problem. If both the trade, because this is a simple example, but in case of more complex issues, or if you try to implement trade for different libraries, so there may be possibility that they may have used the same function signature. For example, like person has my role and programmer has my role as well, and both the signature are matching. So now we have to provide, if you are implementing trade, then this is complaining that not all trade items implemented. We have to, first of all, we have to provide the implementation for both the function, my role. So I am returning a string. In this case, Mr. I am returning, and programmer I am returning Miss. And both are same. I am just passing this, returning this role. This format will just return a role. Format macro will return a formatted string. So if you try to access this emp.myrole, then it will complain, because emp, no doubt it implemented both the trait, programmer as well as person. Using that, you can able to access emp.myname or emp.mylanguage we can access. There is no problem with that. But my role we cannot access, because my role is implemented by both the trait, person as well as programmer. So it got confused which one to call. That's why this error is about multiple applicable items in the scope. So multiple my role found. To solve that issues, we can provide a explicitly name. It is syntax is slightly different, like employee, this struct type, and as person, and the function name, and we have inside this argument we have to pass this immutable difference of employee. If you want to access this programmer, an employee as programmer, then you have to pass the same as employee reference. Then if you try to print my role 1 and my role 2, then in case of my role 1, you will get this Mr. Programmer, because it is referring to person, and my role 2 is pointing to programmer, and in this case MS Programmer. This kind of pattern is very much helpful to provide a same implementation from different to trait. Hope you like my videos, and most of my examples are derived from this Rust by example books, and please check out the links below. Have a good day ahead. Bye bye.